In this video, we want to learn how we can use perfect square identity for factoring expressions. These two identities here are famous to perfect square identities. A to the 2 plus 2ab plus b to the 2 is a plus b to the 2. And a to the 2 minus 2ab plus b to the 2 is a minus b to the 2. But the thing that is very important is that you should be able to figure out for a question, can you use these identities to factor it or not? Look at these examples here. How we can figure out we can use this identity for these trinomials or not. So the first condition is that we have to have three terms. In all of these examples, we have three terms in each of these expressions. The other thing that we have to check is that we have to have two terms that are perfect squares. Look at this first term, x to the 2. This is a perfect square. And look at 9. 9 is 3 to the 2 also. So you have to have in these three terms, two terms that are perfect square. And the other term, this last term, should be twice 2 times by a square root of these two terms. What is the square root of 9? 3. What is the square root of x to the 2? X. Multiply these by each other. 2 times 3 times x is 6x, is exactly this middle term. And attention, for x to the 2, if you take a square root, you can consider negative x. If you multiply these, you would get negative 6x. So here also can be negative 6x. So here can be positive or negative. So in this way, we can check that the expression can be factored by this identity or not. So let us start the first example. First, we write this in the form of x to the 2 plus 6x plus 3 to the 2. Then, we have to check that this middle term is twice of x times by 3. 3 times x is 3x. Twice of that is exactly 6x. By checking this, now we know that this expression can be factored by this identity. This equals to, what is a? Compare this with this identity. A to the 2 is x to the 2. So we have to write x. Then, because it's plus here, so plus. What is b? b is 3 in this example. So x plus 3 to the 2. This is the answer for this example. So x to the 2 plus 6x plus 9 can be factored as x plus 3 to the 2. Maybe you are asking yourself, what is the factored form? We are looking for factors. Basically, x plus 3 to the 2 is x plus 3 times by x plus 3. So this is written in this form, and the factored form of this is this expression. Look at the next example. X to the 2 minus 10x plus 25. Again, we follow same method as the previous example. X to the 2, we leave it as x to the 2 because it is a perfect square. It's obvious. We leave negative 10x here. 25 is 5 to the 2. Now we check for this. Is this middle term the product of these two times by 2? 5 times x is 5x. Times by 2 is 10x. And it doesn't matter. Is it 10x or negative 10x here? If it is negative 10x, then in your answer you would put negative between the two terms. So what is the factored form of this? The factored form would be x minus 5 to the 2. X is a, 5 is b. Based on this identity, x minus 5 to the 2 is the factored form of this expression. Look at the next example. 4x to the 2 plus 12x plus 9. 4x to the 2 is basically 2x to the 2. We leave the middle term, 12x, and 9 is 3 to the 2. Now, this middle term should be twice of these times by this. 3 times 2x is 6x, but here we have twice of that, which is exactly 12x. So we can factor this with the perfect square identity, and it equals to 2x plus 3 to the 2. Before I show you the last example here, let me tell you something. Without the perfect square identity, also you can factor all of these examples with the normal trinomial method. So, without the perfect square identities, we can factor this. Let me show you one of them as an example. For example, suppose we want to factor this. This is a trinomial. X to the 2 minus 10x plus 25. If you remember, for factoring trinomials, we put x in each bracket. Then we look for two numbers that their product is this, their sum is negative 10. Two numbers that their product is 25, and their sum is negative 10. Those numbers are negative 5 and negative 5. Negative 5 times negative 5 is 25, negative 5 plus negative 5 is negative 10. And if you pay attention, if you multiply these two brackets by each other, it's x minus 5 to the 2. This answer is the same answer as we got from perfect square identity. Now, maybe you ask yourself, so what's the reason we should learn this method? Basically, we learn perfect square identity, first of all, as a new method for factoring some trinomials. Because we know the general method for finding factoring form of trinomials. Always we can use those methods. But this is another method, first of all. The other thing that I highly recommend you for factoring perfect squares is that memorize these identity, especially from the factored form to the other side. Because in many examples in math, we have perfect squares like this, a plus b to the 2. You should be able to expand this and write it in this form, in the form of the left side. Because, again, let me repeat this. If we have this and we want to factor it, without this identity also, we can factor with the trinomial method. We learn these identities for the opposite direction, for expanding. Suppose you have a plus b to the 2. Instead of multiplying this bracket by itself, it's very good idea to memorize this, that a plus b to the 2 is this, a to the 2 plus 2ab plus b to the 2. So we had it power 2 here. Now look at the last example here. 9x to the 2 minus 6xy plus y to the 2. 9x to the 2 is 3x to the 2 minus 6xy plus y to the 2. Is the middle term twice of this times by this? Yes, 3x times y is 3xy, times 2 is 6xy, and because here is negative, we have this case. So the factored form of this is 3x minus y to the 2. If you want to see examples like this, and you want to see how we can factor all of these examples with the trinomial method, without the perfect square method, watch my video about trinomials, factoring trinomials. Now look at these examples. These are a little challenging examples. Again, immediately we can see that we have three terms. So we have trinomial here, 100x to the 4 minus 60x to y2 plus 9y to the 4. Immediately we can write the first term as 10x to the 2 to the 2 minus, we leave the middle term, 60x to y2, and 9y to the 4 is 3y to the 2 to the 2. Now we have to check that. Is this middle term twice of this times by this? 10x times 3y2, 10x squared. I forgot to put power 2 here. 10x squared. 10x squared times by 3y to the 2 is 30x to y2. Double it, it's exactly 60x2y2. And because here is minus, we have to use the second perfect square identity. So what is the answer for this? The factor form of this would be 10x to the 2 minus 3y to the 2 all to the 2. Now look at this example. This is a little challenging and different example. We have x to the 2, which obviously is a perfect square. So let me write the x to the 2. And I prefer to put a bracket about for this x, then plus 2. And 1 over x2 can be written as 1 over x all to the 2. 1 to the 2 is 1, x to the 2 is x2. This is basically this term. Now, we have to check that. Is this middle term twice of this times by this? If you multiply x by 1 over x, what would be the answer? X times 1 over x, x with x cancelled, it equals 1. Multiply this by 2, it's exactly the middle term 2. So yes, this is perfect square. And because this is perfect square, we can write it as x plus 1 over x all to the 2. This is the factored form of this expression here. Look at these examples. By looking at this first step, immediately we notice that this cannot be in this form a perfect square because the power is 3. In perfect square, we expect to have even powers like power 2, power 4, power 6, because we need a perfect square. By looking at these three terms, we can see that we have a common factor between these terms. What is common factor between 8, 40, and 50? There is a number common between 8, 40, and 50. 8 is 2 times 4. 40 is 2 times 20. 50 is 2 times 25. So 2 is the common factor between these three terms. So first of all, before doing anything, we factor the common term 2. Then we look at x. We have x to the 3, x to the 2, and x. On all terms we have x, and we can factor just one x. We always factor the variable with the smallest degree. Here we have x to the 3, but here we have x to the 2, and at the last term we have just one x, so we can factor only x from these three terms. And in the first term we don't have any y, so we cannot factor any y from these three terms. So only thing that is common between these three terms is 2x. When we factor 2x, what we have to write in the bracket? When we factor something, a common factor, basically it's like dividing those terms by that term. So we divide these terms by 2x. 8x to the 2 divided by 2x is 4x to the 2. 40x to y divided by 2x is negative 20xy. 50xy to the 2 divided by 2x is 25y2. Now look at the inside of the bracket. Is this a perfect square? We have to check. We leave 2x here. 4x to the 2 is 2x to the 2 minus 20xy plus 5y to the 2. Multiply this by this. 2x times 5y is 10xy. Double it, 20. Yes, we have 20xy here with a negative. So the factored form of this bracket is 2x times y. Leave the 2x outside. 2x minus 5y to the 2. And this is the factored form for this expression here. Look at the next example. Immediately we notice that we have x as a common factor, so we first factor x here. Then we have x times x4 minus 20x2 plus 100. it should be clear for you that x4 is x2 to the 2 minus 20x2, 100 is 10 to the 2. 10 times x2 is 10x2. Twice of that would be 20x2. So this is perfect square. And this can be factored as x to the 2 minus 10 all to the 2. This is the factored form of that expression here. Now look at these examples. These are a little challenging examples. First we have a to the 2 plus 6a to the 2. This is a perfect square. Then 18 times a to the 2 plus 6a, and 81. 81 is 9 to the 2. So let me rewrite this. A to the 2 plus 6a to the 2 plus 18 times a to the 2 plus 6a plus 9 to the 2. Now we have to check that. Is this middle term twice of this times this, 9 times this, double it, 18 times that? Yes. So the middle term is twice of this times by this. So this is a perfect square. Based on the perfect square identity, this equals to a to the 2 plus 6a plus 9 to the 2. But if you pay attention here, the inside is also a perfect square. We have a to the 2, 9 is 3 to the 2. 3 times a times 2, twice of that is exactly 6a. Let me make this a little more clear here. This is a to the 2 plus 6a plus 3 to the 2 all to the 2. This middle term is twice of this times by this. 3 times a is 3a, twice of that is exactly 6a. So we can write the expression inside the bracket using the perfect square identity in this form. We leave the power 2 outside. This expression, focus on here, can be written as a plus 3 to the 2. Now look at this answer. When we have an expression raised to a power, and that power is all raised to another power, we know that based on the power rules, we multiply power by power. So the final answer for this question can be written in this form: a plus 3 to the power of 4. And please attention, what is the meaning of this? It means that multiply a plus 3 by itself 4 times. So this means that this expression can be factored like this, which can be written in this form. Now look at the next example. Pi r to the 2h minus 2 pi r h to the 2 plus pi h to the 2. First, we try to factor the common factor from these terms. Pi is common, we can factor a pi. R, no, we don't have any r as the common factor. This term has no r, but h is common between them. And we can factor only h to the 1, because the first term has only h to the 1. So we can factor pi h, then what remains inside the bracket? If we factor pi h from this goes away and we have only r to the 2. From the second term, what remains? If we divide this by pi h, pi with pi cancels, 1h with h cancels, so we have minus 2 pi rh, minus 2rh. So from the second term, we have minus 2rh. Let me explain this again. Negative 2 pi rh to the 2. When we factor pi h, we divide it by pi h. Pi with pi cancel. 1h with this cancel. We have 1h in numerator. So we have negative 2rh. And finally, from the last term, if we factor pi h, we have h to the 2. Pi h to the 3 over pi h is h to the 2. Look at the expression inside the bracket. It's exactly the perfect square identity. The middle term is twice of this times by this. 2 times r times h is this middle term. But because it's minus here, in the answer we have to put minus. So the final answer is pi h times r minus h to the 2. This is the factored form of this expression here. I hope by watching this video, now you are familiar with the perfect square identity and you know when you can use this identity. If you like this video, please subscribe in my channel and see you in the next videos.